Our next speaker is from Minnesota, and she plays ice hockey. Now, a lot of you know I'm an ice hockey player too, and I appreciate that. So my real question for Erin is, do you do other Minnesotan things like curl? Because if you play hockey and you curl, then we've got to hang out more and go do ice sports. So with that, please welcome Erin to the stage.
Okay, so I think I'm on. Okay, sorry. Here we go. So I think my screen share is also working. My name is Erin LeDell. I work at a company called H2O AI, and I'm going to talk about automatic machine learning in R with H2O today. Here's a little overview of what we're going to talk about today. So I'm just going to do a quick, this is only a 20-minute talk, so I'm going to just do a very high-level overview of what H2O is and what AutoML or automatic machine learning is, and then I'm going to tell you a little bit about the H2O AutoML algorithm, which is inside of the H2O package. So first, if you're not familiar with H2O, you can just get it from CRAN. The package is called H2O, and essentially what it is like it's a machine learning package. You could call it a machine learning platform because it contains a bit more than just algorithms. It's a whole distributed data processing framework as well. So, but just at a high level, so it's a bunch of machine learning algorithms that are distributed, meaning that they run in parallel on your machine. You can also make a cluster of machines where they run across many machines if you have very, very large data. All the algorithms are written in Java, but most data scientists are either R or Python users, so we have an API in R and Python. That's how you would probably use it, just the R package. One of the things that is sort of unique about H2O is that we can export the models as Java code, which is helpful if you're trying to productionize models. That's also not the only way that you can save models. You don't have to deal with anything Java if that's not something you want to deal with. You can do pretty much everything in R, including productionize the models in R exclusively if you'd like. And it's meant to be compatible with sort of big data platforms like Hadoop and Spark. But for the most part, I see just people using it on their laptops as just like a normal R package. So it's really designed for very, very large data sets, big data sets, but you can use it on tiny data sets, you can use it on any size data sets, and it's just a matter of like what hardware you want to use to execute. Okay, so just a bit more about the package. We have supervised and unsupervised machine learning algorithms, pretty much just the popular ones that you would want to use, like gradient boosting machine, random forest, deep neural networks, GLMs, stacked ensembles. We also have a wrapper for XGBoost, which is another GBM. All of these, except for XGBoost, are written from scratch by us in Java in a distributed fashion. So that's kind of one of the differences between a package like H2O and a package like Carrot or Tidy Models, which are really more of like a unifying layer on top of other R packages. So that's sort of one key difference between those two. But for the most part, we have the same goals of just having a unified interface to a bunch of machine learning algorithms and all of the functionality that goes along with machine learning, like cross-validation, grid search, random search, variable importance, model evaluation metrics like MSE, AUC, log loss, etc., and then plots. Okay, so that's just a quick intro to H2O. And then let me just say a little bit about what is automatic machine learning if you're not familiar. So because this is kind of a, let's say, a not well-defined term, I think it's better to talk about what are some of the goals and features of AutoML rather than to focus on trying to define that succinctly. So I think one of the goals really with AutoML is just to train the best model in the least amount of time. So by that I mean time in terms of actual computation time. So how long is it going to take you to train the model once you press go? And then the other aspect of that, which is actually more addressed by AutoML, is how much time it takes you to set up the experiment or the training. And by that I mean, usually you write a whole bunch of code that's like data pre-processing code, then the modeling code, then the model tuning code, a model selection code, and just lots of code being written. And so one of the goals of AutoML is to sort of basically wrap a function around that whole process and just expose the parameters that are, the basic building blocks of what machine learning is. You need a training set. You need to decide which column in the training set are you trying to predict. You might want to decide like which metrics you're interested in. You don't have to necessarily pick beforehand, but like if you're trying to maximize AUC, for example, in a binary classification problem, that's one example. And then essentially the only other thing you need to tell an AutoML tool is like, how long do you want it to run for? So really trying to reduce like the human effort and expertise required in machine learning. I think that's one of the, let's say, goals of AutoML. And also we're trying to give you models that would probably be better than what you could do on your own. Now that's not true of every single data scientist out there. It's, for the most part, humans are still able to beat AutoML systems. Like if you're a very sophisticated data scientist who's been practicing for 10 years or more, and you really know all of the algorithms super well and all of the data domains super well, you could probably still beat every AutoML system out there. So this is really just for, let's say the average or even better than average data scientist. Hopefully you'd still get better models using an AutoML tool. And then one of the last things that I think is nice about AutoML is that it can increase reproducibility. So you really have just this one simple function. It's easy to use. You can get your collaborators to use it. It's easy to use by people that are not sophisticated machine learning people. So that kind of increases your ability to collaborate with people, let's say in a scientific discipline. I think it also is very useful to just establish a baseline for any problem. But in particular, if you're a scientist trying to apply machine learning in a new way, one of the best things you can do is just run an AutoML tool and just see kind of where you're at, and then you try to work up from there. Okay, so the some of the aspects of automated machine learning. Well, when we talk about automating machine learning, we're really just talking about what are the aspects of machine learning, and then we have to automate all those pieces. So that would include things like anything related to data preparation, we'd like to automate. That's actually quite a lot harder than the middle part, which is just the models. Like automating model generation is pretty straightforward. You still have to decide. The hard part about that is how to allocate your time. So if you only have an hour or you only have a certain amount of time, how do you decide where best to apply the work? You probably want to start with models that you think are good or will be good, or algorithms that you think would be good, and then certain settings. So that the real task there, and the real task of any automated machine learning tool, is more about prioritization of what we should try first, rather than something that, it's not anything that somebody couldn't write the code for. It's just it's hard to prioritize when you're given a time frame. And then if your goal is really to get the best model with the least the best model just overall in general, like one of the things that you can do is to create ensembles from the models that you generated. So when you do ensembling, it generally improves performance. There's a few drawbacks of ensembles, which are like, one, it could possibly take more time to generate predictions at the end, and depending on your use case, that might be something you can't have, or maybe it is. So we just let people decide whether or not they want that as part of their process. But if your goal really is performance above all else, model performance, then you should probably be ensembling. Okay, here's some different aspects of automated machine learning in more detail. So with data pre-processing, by that things that could be included in that category would be imputation, one-hot encoding, standardization, different other types of encodings of categorical features. So there's all sorts of different ways that you can encode categorical features, and a lot of it depends on, like, let's say how many features there are, whether or not, how many categories there are, and whether or not some of those categories are extremely rare. Like, there's a lot of things to consider when you choose your encodings, and so, you know, a good AutoML tool should try to optimize that. And then this could also, for the data preprocessing section, we could also just do feature selection or feature extraction, stuff like that. For model generation, there's lots of different ways. Like, a popular way to generate a bunch of models is just a grid search or random search. There's also a technique called Bayesian hyperparameter optimization that I won't talk about, but this is another method for generating models and tuning models. And then for ensembles, the type of ensembling that I generally do is called stacked ensembles or super learning. But there's another one called ensemble selection that also works well, and it really just depends on the type of models that you're using in the ensemble, which one of those will probably do better. Okay, so, and if you're not familiar with AutoML or what software is out there and how do you choose software, essentially it all boils down to, like, what kind of data you have. Do you have tabular data? That's what I'm going to talk about today. That's probably the most common type of data, and there's a whole set of AutoML techniques for that. And then there's kind of a whole nother set of techniques for image classification or text classification related to AutoML. And typically with those types of data, you end up using deep neural networks. So there's a whole field of AutoML specific to deep neural networks, generally referred to as neural architecture search, but it could also involve other things. So I'm not going to talk about that, but if you're confused about the different types of AutoML, I can recommend that you read this blog post that I wrote, I think almost 2 years ago now. Okay, so let me just check my time. I have a few minutes left, 6 minutes. So let's talk about H2O AutoML. So here's the same slide that I had before, but I'm highlighting the sort of our technique as a subset of all the possible techniques out there. So right now we do some basic data preprocessing, and I think in the next version of H2O 3.32, I actually have been promising this for the last couple of versions, but I think for real this time, we're going to get automated target encoding for categorical features in there, and that's going to be a huge bonus to anyone who has especially high cardinality categorical features. I think that's going to help a lot. And in terms of models, what we do is just essentially for each algorithm that we have, we do a random search, and then we individually tune the models using cross-validation. And then once we have the models, we do 2 stacked ensembles at the end. So why do we do this approach? Well, with stacking, so I guess sort of working backwards, when I designed this system, I knew that I wanted to do stacking because I know that that's the best way to get the best models generally. So then in order to create a good stacked ensemble, you need kind of a diverse selection of models to go in there. So one way to sort of generate a diverse set of models is to do a random search, because then, you know, that randomness generates diversity. And basically stacked ensembles do well when the individual models inside, like what we call the base models or the base learners, are individually strong and they make uncorrelated errors, meaning they fail sort of in different ways. So that's why we want to put like a deep neural network and a random forest and a GBM and etc. So that way, that's kind of how the stacked ensemble works. I'm not going to go into a whole lot of detail about that, but just keep that in mind. So that's kind of our approach. There's other approaches by other tools like that are based on different techniques. For example, genetic algorithms, Bayesian optimization, etc. So there's different techniques that people use, and this is just ours. Okay, so this is just sort of the overview. yeah, basic data pre-processing. We train the random grid. We tune the models. We have the 2 stacked ensembles. And then what we sort of get back with after running this function is something that we call the leaderboard. And I'll say what that is in a minute. But first, I just want to show you what the code looks like, because as R people, that's probably what you're here for. And so now you have it. You have a one function called H2O AutoML. And essentially, like I said at the beginning, the very basic things that you need to provide are just what is your training set, what is the column that you're trying to predict, and then like how long do you want to run it for. So here we're running it for 10 minutes, then we're going to take a look at the leaderboard and see what we get. Generally run longer than 10 minutes, but you know, maybe an hour or 4 hours or however long you want. So what the leaderboard is basically just a data frame. And in the first column, we have just the name of the model or the model ID. So these are all just models that are in memory, and you can access all of them. You can look at their hyperparameters, etc. But just to make things concise, we just put the model ID, and then we sort by performance metrics. And for binary classification, by default, we'll sort by cross-validated AUC. So you'll see all the models that we've trained on there. We see the stacked ensembles winning. That's pretty common. Then we see a few XG boosts and etc. down the line. And so how do these tools really do compare to humans? So I brought that up before. So like I said, I think if humans have enough time, they can beat the AutoML tools. However, if it's really kind of like a short time period, like so Kaggle had this 1 day, well, let's say 8-hour Kaggle competition, and basically, you know, all the AutoML tools were winning. So that's unusual for Kaggle because, you know, if you have a 2-month competition, people spend a lot of time on feature engineering. They're very creative and they come up with all these things, and they're able to win. But with just a 1-day competition, like I was just able to run H2O AutoML for, I think it was 100 minutes. And I got 8th place in the competition. So I literally basically did nothing. I just loaded the data set, ran it, and then submitted my result. So that's, yeah. So in a short time frame, I think if you're training models every day, like this is something that can immediately help you. And then if you want to learn more, I finally got around to publishing a paper about H2O AutoML just last month. The tool has been out there for about 3 years. You know, I spent a lot of time on documentation and things like that and not so much time on a paper, but I did finally write one. So if you want to read more about the algorithm and see how it scales, I did a study from like data sets of 10,000 rows all the way up to 100 million rows. And that's on a single machine, by the way. So we are very able to scale well, basically. That's why you know, building an AutoML tool on a library like H2O was appealing to me, because the base models themselves or the underlying models are quite fast. So I only have 1 minute, so I'm just going to leave you with a few links. The last one is a talk that I just gave at the USAR conference last month, and this is all about responsibility of data scientists. So the title was like responsible automation, and like how do we be responsible humans when we're building these AutoML tools and just machine learning tools in general. So there's a lot of discussion about interpretability and algorithmic fairness and stuff like that. So I think I'm out of time, so I will just leave you with some contact info and a shout out to our leads. We're just gonna stop there.
Cool.
Thanks, Jared.
Thank you for speaking. And yes, notice the strong R Ladies presence here. There's always been a good showing. Thank you all for coming. Thank you everyone for coming.